The role of internet checksum at the transport layer has been well understood. But as we said earlier, data link layer replicates the functionality that is also offered at the transport layer in a link-by-link manner. In this module, we shall explore checksumming methods that are incorporated at the data link layer. We'll start with an appreciation of the overhead of single-bit parity schemes, which provides us a motivation to move on to more advanced checksumming methods. We'd look at the basic idea of checksum. Then we'd look at the operation of checksum, and we'd look at how checksum at the data link layer is different from the checksum at the transport layer. The references I've chosen for this module are shown in here. The overhead of parity schemes is the obvious reason that motivates us to move on to more advanced parity scheme or error detection mechanisms. Let's take the example of single-bit parity scheme. If single-bit parity scheme is to be implemented for every ASCII coded representations, then we'd have 7 data bits plus 1 parity bit. It means we are going to have a redundancy of around 12%. To provide enough resilience, we need to have more redundancy. And if we keep on increasing the bits as in single bit parity scheme, this would become unaffordable because we are mainly interested in sending data, not unnecessarily adding wasteful redundancy to it. So the solution is we take k-bit integers and we sum them up, manipulate them, and finally we only generate k bits of overhead. This is the basis of checksum. RFC 1071 proposes basic details of checksum and suggests to use the alternatives as well. The most important or the underlying concept of checksum is we sum all the k-bit integers and the resultant sum is converted into 1's complement. For instance, the 16-bit checksum in TCP and UDP that we discussed earlier is based on this concept. And then these checksum bits are added or appended with the data bits and sent over the communication medium. With this basic idea of checksum, some variants exist depending upon how they are used and on what they are used. For instance, in TCP and UDP, the checksum is computed on all the fields including the header and the data. In an IP datagram, only the IP header is implementing the checksum. And there is a reason to that, because of a router that receives an IP datagram is only interested in processing the IP header. It is not interested in checking what data is being sent within that IP datagram. Protocols such as XTP use two-fold or 2 levels of checksum. The first one is computed at the header and the second one is computed over the entire packet. Although checksum is being used at the transport layer, what checksum strategies are used and why they are different at the data link layer? The answer to this is that the transport layer is an upper layer protocol and it is mainly implemented through software. So the checksum procedures which are implemented in the software have to be lightweight, otherwise the computational complexity is going to become uncontrollably large. This is not the case at the data link layer, because as we said earlier, data link layer functionality is implemented through the network interface card. So more complex and advanced checksumming methods such as cyclic redundancy check can be utilized. which are more robust and which are handled by the dedicated hardware or the LAN card.